Hello, everyone. Until the last lecture, we have discussed gas power cycles. But from today, for 2 lecture hours, we are going to talk about vapor power cycles. Particularly today, we are going to learn about the Rankine cycle. Please, before you watch this video lecture, please read the reading assignment from chapter 10.1 through 10.3. By the end of this class, I really hope that you can answer those two questions. So I really hope that you can draw the TS diagram of the Rankine cycle and also can conduct the cycle analysis. And second thing that I would expect from you is that you really hope that you can consider the isentropic efficiencies of the pump and turbine in the Rankine cycle analysis for actual Rankine cycle analysis. Before we move on to Rankine cycle, then I really want to review what we learned on the last lecture. So we learned about the actual Brayton cycle. So there are two loss factors in the actual Brayton cycle. The first one is the pressure drop because of friction, and second one is irreversibilities in the compressor and turbine. And both two factors, lower the power and efficiency. So by looking at the TS diagram of the actual Brayton cycle, which is shown as green dashed curve. So as a result of these two loss factors, the overall area surrounded by four processes are shrink from the ideal case. So by the amount of shrink, then that means that we lose some power. And at the same time, because of those loss factors, the thermal efficiency of the Brayton cycle is also lowered. So then how can we compensate this lost power and the efficiency lowness? The first thing we can consider is to use a regeneration gas turbine. And the purpose of having the regeneration system in the gas turbine is to improve the thermal efficiency. So the core is located in placing a regenerator or a heat exchanger at the end of the turbine exit gas, such that still the hot exhaust gas can transfer its heat to preheat the air that comes out from the compressor. So as a result of this heat transfer in between, we can save a certain amount of heat by transferring the heat from the hot exhaust gas to the air side. So instead of the burning of fuel to increase the temperature of the air from 2 to 3, we only can increase the temperature at 5 to 3 if we have a regenerator. So what it means is that we can save some fuel and save the energy that should be used to heat up the air to the temperature 3, and as a result, we can save the thermal efficiency. Then how about improving the power output? So in order to increase the power output, we can think about using the reheating and also intercooling. So instead of having one compressor and one turbine, we basically can use multi-stage compressors and multi-stage turbines. And this diagram, schematic diagram, describes the one example of two-stage gas turbine system. And between the compressor 1 and 2, we have intercooler. And between the turbine 1 and turbine 2, we have reheater. So by cooling down in between the compressors and by reheating your gas in between two turbines, we can actually increase the net area surrounded by all these processes. So what it means is that we can increase the power output. However, because we need more heat input to run this two-stage gas turbine, the result is that we should lower the efficiency. So now, in order to compensate this efficiency loss, we also can integrate the regenerator to improve the thermal efficiency as well. So that is quite complicated system, but that is the way that we can improve the power output and the thermal efficiency at the same time. Now, as I said before, today I'm going to talk about the Rankine cycle. So Rankine cycle is a base thermodynamic model for vapor power plant. So basically from today's lecture and the next lecture, we are going to talk about how we make use of vapor, particularly steam mostly, to use it for power generation. Then now the next question, the naturally coming out question is why water? Why are we interested in using water as a working fluid? So the first answer that we can simply can make is yes, water is very abundant and very cheap. You can find water literally everywhere, and also is very cheap. And at the same time, water is very stable chemically. It's not toxic and it's not almost corrosive. So we can safely use water without worrying about the toxicity or corrosion during the power generation system. And also, you can easily, vaporize water. So in other words, you can boil it and you can generate the steam. And steam is quite, we have to use a steam to run the turbine. Okay. So that is another very important advantage that we have to think about. And one more thing that we usually, don't remember or just, overlook is the water has very high density. So what it means is that we need less compressor work to compress the water. Okay, that is another big advantage of using water as a working fluid for a vapor power plant. Even in the ancient Greek time, people already knew that if they generate the steam from water, they could make use of that the high pressure steam for certain things to rotate or move. And what you see in this slide is one good example of that kind of device. That is called as Heron's airlift pile. Okay, that's pretty hard to pronunciate, but that is quite kind of toy. Okay, and how Heron made, what Heron made is now he filled up a half-filled water inside sphere tank, and there are two exit pipelines. They just burn wood to make a steam from water that is filled in that the sphere tank. And once this steam is generated, then steam goes out from this sphere tank via these two pipelines, and that makes a force to rotate this sphere tank. Okay? But that is just a toy. Okay? And it should take a long time until people realize that this kind of power could be used for our own benefit. Okay? That happened in 18th century. Okay? And James Watt in 1765 made a first steam engine. Okay? Then people were so excited by looking at the possibility that they could use steam for certain things that would be beneficial for us. Then people invented a lot of other kind of systems or devices. And then one first example is the steam engine vehicle. Okay? The first steam engine vehicle came out in 1769. That is only 4 years later, James Watt made a steam engine. But its speed was amazing. Okay? The speed was 2.5 miles per hour. Okay? Still, riding a horse could be much faster than riding a steam engine vehicle. But that is really meaningful because that was the first thing that people invented to ride instead of riding a horse or other living creatures. And then people kept using these steam engines and improved the steam engines. And in 1814, then Stephenson made a locomotive engine. Okay, and his record, the record of his engine was 29 miles per hour. So within around 50 years, the speed of that vehicle that used steam engine increased from 2.5 miles per hour to 29 miles per hour, which is more than 10 times faster. Okay. Then where do we use, yeah, okay. And then also people thought about using that steam power plant or steam cycle for power generation. And the Fisk generation station was built in 1903 in Chicago, Illinois. That was the first modern power plant that used a steam turbine. Okay. And this power plant used 5 megawatt turbine generator. And that was a huge, monumental success as an engineer, effort. Okay. This power plant is not being used anymore, but that was the kind of the evidence then how far engineers can go to help people in generating power. In these days, steam power plants are being used in many different areas, okay, and in many different types. The first thing that we can easily see is a fossil fuel power plant. And in that case, we burn a fossil fuel such as coal or oil to boil a water to generate a steam. Okay. There is another type of vapor power plant, which is solar thermal power plant. You probably saw this power plant if you had a chance to drive to Los Angeles, California. And as soon as you pass the borderline between California and Nevada, then you probably saw on the right-hand side that there's a bright tower with and surrounded by a lot of meters. And that is a solar thermal power plant. And what it does is surrounded by a lot of meters, and these all meters reflect solar light to one point in the center line of and on top of that tower. Okay? And usually the concentration ratio is like several hundred or even thousand. Okay? That solar concentration is so huge and so intense to even melt salt. Okay? And this molten salt can go down to meet a heat exchanger where heat is transferred from molten salt to water to generate a steam. And this steam runs steam power to power the generator power. Okay. What else? The another thing that we make use of vapor power generation is nuclear power plant. Okay. In that case, then we use a huge energy from during the nuclear fission process, and this energy can be used to generate a steam from water, and also we run a steam turbine to generate the power. So by looking at those three different types of power plants, we still have a common thing. We want to generate a steam to generate a power, okay, by running a steam turbine from this by using the steam. But how we make a steam is different. By using fossil fuel or by using solar energy or by using nuclear energy. So that is only the difference. So now let's take a look at this steam power plant, a little more. Okay, so steam power plant itself is really complicated, and that actually has in big like 4 big parts. One is more likely combustion, inside the boiler, where we burn out of fuel. And A is a kind of core part of steam power plant, where we have steam generator, okay, which are installed in a boiler to generate water to steam. Okay? And steam runs a turbine, and after expansion process, then steam goes to the condenser to be condensed to water, liquid water, and this water goes through the feed water pump to increase its pressure. That's what we are going to learn in today's lecture. Then this turbine is connected to an electric generator, and from this electric generator, then we can generate the power, the electricity. In terms of a condenser, how can we condense a vapor, water vapor to water liquid? Because we need to release heat, reject heat to water, okay, another water. So that is what happens by using the cooling tower and by circulating cold water through the condenser to take heat away from the water vapor. Okay. In our textbook, this overall condensing process using a cooling tower is discussed in chapter 14, and the chemical reaction through the combustion process and its thermodynamic analysis is discussed in chapter 15, but that is outside our scope in our class. So we are going to mainly focus on this cycle. So let's take a look at how each component of this cycle actually looks like. Okay, so that is a boiler. Okay, and boiler is kind of big, gigantic kind of building, and you see on the right hand side figure that is the boiler. Okay, and there is a huge size that is almost a 4-story building. Okay, but what's inside is a lot of pipelines are surrounding on the inner wall of the boiler. Okay, and that is what we see. So that is inside the boiler wall, and as you see, there are a bunch of like a lot of pipelines that is installed. Okay, so in the middle we have kind of fuel burning, right? Then this big kind of combustion process delivers heat to the pipeline and water flowing inside the pipelines to generate a steam. Okay, and then do you see how big that boiler is? And people are working on a boiler wall, and that is those are 2 people. Okay, so that is how huge that boiler system is. It's not how it works is the same, but the size wise is totally different from a boiler that you have at your house. Okay. Then how about steam turbine? Steam turbine is also really big. So that is a high pressure steam turbine, and that is a low pressure and intermediate pressure steam turbine. And you see people here and here. So that is a really huge size power plant. Okay, and if time allows, I really strongly encourage you to visit or I don't know how you can, but still, I really truly wish that if I have a chance, then I really would like bring you to those kind of power plant or those steam turbine manufacturer to show you those kind of all manufacturing processes. But unfortunately, I don't have any network, so just I hope that you can enjoy appreciate those kind of power plants and those kind of steam turbine manufacturing processes by looking at those photos only.